All right, okay, welcome. For those who made it in person and those who are online. So I guess that's day 2 of the training week. Today we are going to take you through how you can do and learn about free energy calculations, and particular kind of free energy calculation called alchemical free energy calculation, and that's using a software called BioSimSpace. So quick schedule. We'll be busy until about 12:30. We're going to have a quick intro lecture. And then the plan is to have you have a go at an intro tutorial, just to get familiar with the basics. And after the coffee break, we've got 2 other tutorials. Choose the one you want to work with. If you have no preference, you can start with the relative binding free energy one. Or if you already have interest in absolute binding free energy, go straight to that one. If you go fast, you might be able to do both of them. If not, everything is available online and will remain available, so you can also look at that later on. So quick word about ourselves first. So this tutorial is delivered by BioSim. BioSim is a software company that promotes use of open source research software in academia industry. And if you want to know a bit more about us, you can look us up on the web or LinkedIn or GitHub and places like that. So in terms of using the resource for this workshop, there's everything is available at this URL on github.com/openbiosim BioSimSpace tutorials. There's 2 ways you can complete the tutorials. You can either install locally BioSimSpace, which require some familiarity with Conda, which might be the best way moving on if you want to keep experimenting with that tool. And if you got that set up already because you saw an email a few days ago, that's great. If not, we would recommend by default for today that you try to follow the workshop materials using our Jupyter Hub server at try.openbiosim.org, which should work with basically, hopefully, any web browser that you have on your laptop. And then all you have to do is type this URL into your web browser, which should fire up after 20-second window that looks like this. Then double-click on the file tutorial.txt, which will prompt you to type a line of code to clone the GitHub repository from the command line. For that, you also need to open a terminal here. Okay. If you've got issues with that later on when we get started, just raise your hand or drop a line in our chat. So a few words about what the tool you're going to work with. What is BioSimSpace? BioSimSpace is it's basically a Python library that's been developed to make it easier to connect different biomolecular simulation software into potentially scientifically useful workflows. So this project has been going on through various funding streams for the last 5-6 years. It started as an EPSRC grant for a project led by CCPBioSim. What it does mostly nowadays is give you access to a Python interface to do certain common tasks that occur repeatedly in biomolecular simulation studies, like parameterizing a molecule, solvating a protein in a box, running MD simulation via different engine, and there's also a support for various kind of alchemical free energy engine, which is going to be the focus of today's workshop. So a couple of words, alchemical free energy methods. So what we're talking about here, if you're not too familiar with this, the problem class we're interested in here is in drug discovery. for projects that benefit from information about the structure of a drug target, it's often helpful to use the structural information to guide the selection of optimal substituents around a particular small molecule scaffold. So you see an example, a depiction of a protein called type 2 kinase. And this is a library of generic inhibitors. And basically what we want through alchemical free energy method is take this data as input and produce as output some kind of plot like this. This is a case where things have gone well, where we can predict free energy of binding for this series of compounds, and there's a good correlation with experiments. So we can use the methodology to prioritize compounds for actual real-world experiments. So this kind of technology has become much more popular in the last 10 years. And then this timeline here is just to highlight that it's what we experience today is really the result of almost 100 years of academic research. So just to be a little bit more specific here, what are we interested in? We're interested in computing these quantities, the free energy of binding for the reversible association, non-covalent association of a small molecule to a big molecule. That we can relate that to a binding constant, which in a sense tell us in certain reference condition what is the probability that you observe your system of two molecules together or separated. And what we need is an efficient computational framework to be able to estimate this quantity, and that's how we can connect simulation with experiments. So simulating the direct pathway that would happen if you measure a binding constant in a test tube, which implies diffusion of molecules in and out of the binding site on relatively long time scale, would be inaccessible by typical atomistic simulation method. So we use here a shortcut to make this calculation more efficient. So what you have here on this axis, this is on the binding process, the real world binding process, where you start with a molecule in solvent and intend a complex to a host. And this is a related molecule, which has a different free energy of binding. We don't attempt to compute this quantity directly. What we do instead is we use a trick to alchemically transmute molecule A into molecule B in a solvated environment or in a binding site environment. These give us two quantities here, which we can determine from our simulation, which we cannot relate to any experimental observable, but we can then close the thermodynamic cycle here, rearrange it such that we can express the difference of the experimental quantities as a difference of these computed quantities. Now, the benefit is we bypass the complicated simulation that would involve simulating the whole diffusive process. So that makes this calculation much more efficient and therefore can be deployed at a scale. There's various tricks that must be followed in order to implement successfully an alchemical free energy calculation. And one of the most important concepts is that of the so-called Lambda coordinate. And in order for this free energy estimate to numerically be reliable and converge on accessible time scale, we cannot alchemically transform molecule A into B in one go. We have to multi-stage the transformation passing through a series of intermediates. So what you see here, we've got a molecule of benzene here that is gradually growing additional hydrogen atom and a carbon atom and a hydroxyl group here. So we can mathematically express this using a lambda variable, which at the state 0 describe our initial molecule, and at state 1 the final molecule, and anything in between is some kind of interpolation. There's various ways you can actually implement the interpolation, but fundamentally you do need to be able to have a continuous description of the alchemical transformation to be able to implement this. So we need then for also ways to compute energies of these molecules at any different alchemical states. So we use typical force field for that, which you're probably already familiar in some way or another. There's various technicalities that need to be overcome with this calculation, and they're related to the appearance of atoms. So we can't actually really annihilate atoms in simulations. We cannot make them disappear. They have to be present. But when the initial and final molecule have different number of atoms, we have to construct an artificial molecule with non-interacting atom in one state. We call these dummy atoms. And dummy atoms can cause problem because at some point they have to stop becoming dummy atoms, and suddenly they have to exclude volume in space because somehow we have to pretend they're here at this point, and that can create numerical instability in simulation and slow convergence of free energy change. And so it is important to use techniques like soft core potential, which modify the strength of the repulsive interaction between particles involving dummy atoms so that they can more smoothly appear without pushing away suddenly lots of particles in the system. So in BioSimSpace, we make this construction by starting from chemical representation of molecules that would be generated by standard simulation pipelines. And then make a decision that we will mutate one molecule into another, and then create behind the scene what we call a merge molecule, which has this ability to smoothly represent either end state. And that's a bookkeeping of knowing which parameter you should be using and how to update the parameter as a function of lambda. So we can use BioSimSpace to set up alchemical free energy methods for different class of simulation engine. So fundamentally, the process of mapping is somewhat engine agnostic. So we can make these decisions. And then when we decided which atom is mapping onto which other atom, we can write down input that are specific for different MD engine. So you may be familiar with MBAR, and there's a training session tomorrow, or Bromax, and we also have support for other engine like Sandy that was developed in my group. Then we typically, once we set up the input files with BioSimSpace, we typically execute them through some form of workflow engine, generate the simulation data, and then bring this back in BioSimSpace for standardized analysis. So if you do calculation where you take a molecule of histidine, say, and you transmute it into methanol, that would give you a free energy change, which we obtain by running a set of independent or loosely coupled MD simulation at different lambda values. We get trajectories of energies of our system. Now, how do we relate that to a free energy change? There's various theory to do this. The most established one that's obsolete nowadays, but easier to understand, is a so-called Zonding equation, which tells us that the free energy difference between state A and B is given by this equation, which tells us that we can estimate that if we run a simulation over state A and calculate the average of the exponential of the difference of potential energy between state B and A. Now, to implement that for a simulation with multiple lambda values, we would calculate first the free energy change for lambda 0 to 0.25, and 0.25 to 0.5, and so on, and sum all these values. There's other ways to approach the problem. One can also use thermodynamic integration, which basically then express the free energy change as an integration over free energy gradient, and it can be shown that the derivative of the free energy with respect to lambda is actually an ensemble average of the derivative of the potential energy, which kind of gives you a plot of free energy gradient here. And then we can simply use various numerical methods to integrate the area specified by this function. And that also gives us the free energy estimate. Nowadays, practitioners frequently use a technique called Bennett acceptance ratio or multi-state Bennett acceptance ratio. So you will see some example of that in the workshop today. So BAR is basically, you can think of it as a variant of the Zondig equation where you simultaneously analyze energy difference coming from a simulation at state A and state B. Now there's a little bit of a wizardry here through the use of a function f that is chosen to minimize the standard error of the free energy estimate for a finite number of samples. And seminal work from Bennett back in 1976 actually showed that if you use this function f and you set a constant c to the actual free energy of interest, you minimize the standard error. What that gives you is that it's an equation that must be solved self-consistently because you do need the answer of the quantity of interest, delta G, show up in the equation on the right-hand side. And so to do that, you need to solve it iteratively through a procedure like this. And you can think of MBAR as essentially a generalization of BAR that attempt to use simultaneous information from all possible pairs of windows rather than a pair of windows at a time. And that has some additional benefit over BAR. Yeah. Another concept that you'll come across in the workshop today is that of the overlap matrix, which is a tool to diagnose the quality of an alchemical free energy calculation. You can think of this as a measure of the probability that a sample that is observed at a value of lambda would also be part of the distribution of samples that occur at another value of lambda. So when you plot this, you imagine you've got a set of here we've got 8 different windows. So you can look at the probability that sample from your distribution at state 0 would also show up at a simulation at state 1 or 2 or 3, 4. Typically what happens is because of the way we build the lambda coordinates, the states that are closer in lambda are more similar. And so there's a greater likelihood that whatever they've seen in their simulation is also relevant to what you would have seen in a simulation at a nearby lambda value. So you often end up with this kind of 3-diagonal structure where the probability rapidly vanishes. Now, you can use that to diagnose, for instance, whether the positioning of discrete lambda value that you set up in your schedule is optimal. You do want to ensure that there's a reasonable amount of space overlap between neighboring lambda values. Otherwise, that translates into poor reproducibility of your energy estimate. Okay, and so that was the crash course in alchemical free energy calculations. And at this point, the best way to get going further is to get started with the introduction tutorial. So either on your local Conda install or by logging in onto our Jupyter Hub server, try.openbiosim.org, follow the tutorials installation instruction, which will allow you to create the folder BioSimSpace tutorial. And there's many tutorials in that repository. We're not covering all of them today. So the first one that you want to work with in the folder 04 FEP and subfolder 01 Intro to Alchemy. Okay.